Hello everyone, welcome to a new video. This is part 2 of the series about mixture of experts, where we just go through this article by on Hugging Face and try to understand this beautiful concept of mixture of experts. In today's video, we are going to discuss a lot of interesting topics like sparsity, load balancing, and the internals of such an architecture. We will go we'll go into the fine-tuning section in the next video. So let's start with this video and I hope that you enjoy this. I'll try to explain the concepts in very simple terms so that it is easy to grasp. And always you can I'll share this link to the blog in the description. You can go through it and read it yourself as well. So let's start. So a brief history about mixture of experts goes like the roots of the paper are from the research paper Adaptive Mixture of Local Experts. And then between 2010 to 2015, an interesting development happens in parallel. First one is mixture of experts as components by deeper network, allowing MOEs to be layers in a multi-layer network, making it possible for the model to be large and efficient. And this work is by none other than OpenAI founder Ilya and by others like Eigen and Ranzato. And in parallel, there was this person, Yoshua Bengio, who researched approaches to dynamically activate or deactivate components based on the input token. A short description of this is as you can see on the screen. Now let's go on to the next section. The router math, an interesting part. See, the concept is known as sparsity. As we discussed in the last video, sparsity is nothing but choosing the right expert for the right token. What does that mean and how does it help? Let's say you have three experts in your network and let's say a token. Let's let's say this token is for a coding input and the experts that you have is one a geography expert, second is a coding expert, and third is an English expert. Now, if it were a normal architecture, this input token, which is a coding token, would have to go through all of the layers and then get finally become an output which we give it to the user. This obviously increases the computation cost because all the neural networks that you have are being used in order to process only a small coding token. The alternative is for this is like where you have individual experts based on their specialty. So whenever an input token comes, the router will route this input token to the respective expert. In this case, expert number two, who is a coding expert. This way, you save a lot of computation cost because experts 1 and 3 will not be activated, only expert 2 will be used, and hence you you just utilize those uh, n number of parameters that are in expert 2 rather than using the whole network. This concept is known as sparsity, as we had discussed earlier, saving you a lot of computation cost. The mathematical representation is shown on the screen, where g of I is the softmax function. Now, for those who don't know what is a softmax function, it basically calculates the probabilities based on the raw inputs that is known as the logits, using which you can determine which expert the router has to route the token to. Now, how does the router decide which ones it does not have to send the token? It's very simple. You just the softmax function just calculates it as zero, and then those experts are entirely skipped, and you save the computation cost. The challenge for such an architecture is that, let's say for some reason, your router favors expert number two. For some reason, let's say it has a faster inference or it has a lower loss or something. The result of this is that the router will favor or will always favor or continue to favor expert 2 for the tokens and leave expert 1 and 3 as it is. Now, the analogy for this is that let's say you are working in a company and you have two interns, intern A and intern B, right? And then you have, let's say, 100 tasks to assign. And for some reason, you favor intern 1. What will you do as a human being? Naturally, you will give all the tasks to intern 1 because he is able to finish the task earlier rather than intern 2. Now, at the end of 6 months, the result of this is that intern 1 has a lot of experience because he has worked on around 70 to 80 tasks out of 100, and naturally he will gain experience and uh, better knowledge of the things. But on the other hand, intern 2 will have worked only on 20 to 30 tasks, and due to which he will have a lesser experience, and hence he will be lesser employable, or he has a lesser skill. This is one aspect. The second aspect is that if you just route all your tasks to intern 1, won't he be overloaded and intern 2 be underutilized? Similar thing happens in the case of mixture of experts, where if the router favors one expert, it will be overutilized and the others will be underutilized. And hence, let's say all these, in our previous example, let's say all of the tasks were related to front end, and the intern one will get trained on the front end task, right? And let's say you have an input token which requires a backend task to be done. Whom do you assign? Intern 1 is trained only on front-end tasks and intern 2 does not have any experience. So you are stuck in this situation, right? Similar thing happens with the routers, where if we just favor one expert, it will be overutilized and others will be underutilized, as well as they won't be trained particular for different number of things, and this will just negate the whole concept of mixture of experts, where we wanted to have individual experts which individually has different sets of specializations. The solution for such an approach was initially explored by a person known as Shazir, and the solution was known as noisy propagating, where you intentionally add a noise to the system. What does this noise mean? Basically, you randomize or add some loss to the uh, output loss, prediction loss. Like if you know, whenever we train a model, we have a parameter known as prediction loss, based on which we determine if the input and the output, that is the output and the expected output, the loss between them determines how good our model is, right? So we add a noise so that it encourages exploration and load balancing, which in simple terms means, let's say, whenever we give a task to our intern 1 and it produces an output, or it has a probability of giving the output of 0.98, let's suppose 0.98 out of, and the maximum probability is 1. By adding a noise, what you do is you reduce the probability of intern 1 by some amount and increase the probability of intern 2 by some amount, due to which, from your perspective, both of them will appear, I would not say equal, but like both will be equally likely to be able to perform the task. So the next time, whenever you get a task, you are not inclined towards intern 1, but you can actually provide intern 2 as well, give intern 2 the task as well, so that it is able to train and get knowledge. So it encourages exploration, and due to this, initially, since we had 70 tasks to intern one and only 30 to intern two, in the second case, when we add some noise, intentionally add some noise, we provide 50 tasks to intern one as well as 50 to intern two. This way, both are able to get enough examples to train on, and both are able to develop their own specialties based on the input tasks. Similar concept is in the mixture of experts as well, where you provide enough tokens to all the experts so that each token is able to cultivate their own specialty. And this loss is in the form of a prediction loss, which we will uh, look into ahead. But this is an overview of what adding a noise means. And then once you add a noise, you have this top k, that is you at max, let's say after you get the outputs from each tokens from each experts, you have a gating network which evaluates the outputs, and then it will uh, choose the outputs from the best one or two experts based on the input token. And this is also decided based on the softmax function and that is the probability that we calculate, and the best top two experts will be chosen. Now, there is also some interesting points to be noted here. Now, let's say during inference, that is once you train the models and then you get them on the actual work. Let's say if sometimes the softmax function produces nearby probabilities for 3 to 4 experts. What do you do in such a case? So in that case, you basically combine the outputs of these experts and then produce a single output and give it out. But like this was the primitive approach, and later on further research by Google, they found out that uh, they found out that even k equals 1, that is, you choosing only one expert also produces a better quality rather than combining all those experts. So this way you save the compute and you produce the same good quality output. Another interesting property of the sparsity concept or the noisy top key gating concept is that during during inference, if you have a low value of k, that is 1 or 2 at max, you will have a much faster inference. Why is that? Because you just have to combine the inputs from two experts rather than a whole set of 8 to 10 experts, right? But the reverse is true when during training, because again, the interns example, if you just favor a few experts out of a whole set of experts, then the others won't be trained sufficiently, and hence you will degrade the quality of the model. Hence, during training, you will have to keep a a bigger value of k, and during inference, you just keep one or two experts so that your inference is faster. As discussed earlier, if we don't balance the load, the routers can collapse because popular experts we train get trained faster and then we become even more popular, causing overutilization of some and underutilization of the others. To balance this, we have we add a loss to the function so that we encourage uniform training of all the experts. This loss is called as auxiliary loss, and there is a mathematical representation to this as well, which we will look into ahead. Now comes the big daddy, which is who is called as GShard. The GShard architecture by Google, or it is also known as the switch transformer. What it essentially does is that one, it uses the MoE concept, and that is having mixture of experts. A second interesting thing that they do is, like, let's say you have to scale, like this architecture is very scalable. Why is that? Because let's say you have n number of devices, and by devices I mean servers, which hold your model. So what they do is, instead of having all the experts, let's say 10 experts in all those 10 or n devices, what they do is that every device will have only one expert. But whenever during training or during inference, all these experts will be accessible to all these devices. What do I mean by this? Let's say an input token in device number 1 requires expert number 7 in device number 7. What does it do? Like Normally, you would have to have these 10 experts in all the 10 devices, and then so that whenever the token requires expert number 7 in device number 1, it will have to route, it will go through the, like everything, every mechanism will just go into, will just happen into in the first device only. But this approach is not scalable because this will consume a lot of RAM. As you know, experts have to be loaded on RAM. Hence, it will increase a lot of computation cost, and this architecture is not scalable as well. So, what is the other approach to this? The other approach is that you have you have n number of experts fitted into n number of devices. Yes, each expert will have each device will have an expert, and whenever an input token, let's say in device number 1, an input token requires device number 7, it will get routed to device number 7, which has the expert number 7. Using this, you can theoretically scale to thousands of devices as well as thousands of experts because you have just decoupled the expert from the device. Any token can route to any device which has the required expert. So, formally, this GShard architecture replaces every other FFM layer with an MoE layer, and it uses top to gating an encoder and decoder. It adds a random seed expert routing for balance. A random seed expert basically means the concept where we route the input token towards the expert or the device that it needs. So this also introduces expert capacity for fixed tensor shapes. What does expert capacity mean? We'll discuss ahead. Now, in this diagram, if you carefully observe, you have two jargons here, all to all combine and all to all dispatch. This is just a jargon, and what it essentially means is that you just route the token, input token to its respective expert in the respective device. This is all to all dispatch, and then when the output of that token, let's say in the example, the input was in device number 1, but the expert was in device number 7. So when the expert number 7 produces an output, we'll have to combine it to device 1 and then produce the output. Right? So this is called as all to all combine. Nothing too fancy here. Also, one thing I would like to share here is that for the ones who don't know, encoder uh, don't know the difference between encoders and decoders. Encoders is basically something that understands and represents the output, whereas decoder is something that generates the output step by step. Encoders basically process the whole input and produce representable vectors. While going through all of these concepts, if you were like me, you would have this question, like each token can have a different meaning, right? Like let's say in English, any word can have multiple meanings based on how it is used. That is, the concept is important for each word. Now, if we individually route each token to an expert, how does the model know what is the context in which the word was used? Like, at least I had this doubt. So, the answer to this lies in the concept of attention layer, where when we like when we convert an input word to a token, we just don't mathematically represent it in a random way. Instead, what we do is we take the whole input and then represent the whole input in such a way that every token has the context of the whole input. And this way, whenever you route the token into a expert or a model, every token has the context of the whole sentence or the whole input. And that way, you don't just ran produce random inputs or random tokens. Every token has meaning, and the magic lies in the attention layer, which is a beautiful concept in its own and something to be discussed in other videos. So, Encoders uses this attention layer and produces meaningful tokens. And then, what is a decoder? A decoder basically predicts the outputs step by step, and it has two mechanisms in here. One is the masked attention, wherein it just refers its already produced tokens to predict the next token. And second is the cross attention layer or the cross attention mechanism, where the decoder uses masked attention, uh, as well as the cross attention is basically it refers to the encoder's output, so that it has the context of the whole input, and hence based on that context and the tokens it has produced till now, it will produce the next token. So this was just an overview of encoders and decoders for those who didn't know or didn't have clarity on. Let's move ahead. So what is expert capacity? Like, as you can make out from the name, we assign a fixed capacity to each expert. What fixed capacity? The fixed capacity of tokens it can process. Why is that? Because experts or these machine learning models work on GPUs, and as you might know, GPUs have, just like we assign a fixed size of an array in C++. Similarly, for maximum efficiency, GPUs have to be pre-assigned a fixed weight, because they do batch processing. That is, they have a fixed size and they do batch processing parallelly for maximum efficiency. And due to which we have to pre-assign a capacity for each export. Now, what are the results or what are the consequences of such an approach? Let's say the expert has a capacity of 10 tokens and we provide it with 14 or 15. What happens is that 5 tokens are overflow tokens. Now there are two options to this. Either you altogether drop the overflow tokens, or just like we do in switch transformers or the GShard architecture, they pass it on to the residual connection layer, and then it goes ahead. This and then it gets combined with the output from the exports, and you produce a single output. Using this, like, these are just approaches to handle overflow tokens. Nothing too fancy here. And a mathematical representation is that capacity is the tokens per batch and the exports into capacity factor, where capacity factor is usually has values of 1 or 1.25 or 1.25. Each export receives a fixed token. If the export is full, overflow tokens are either dropped or passed onward. Higher capacity factor improves the quality, but it will obviously raise memory and all-to-all traffic. Now let's start with this interesting architecture by switch transformers by Google. They simplify the architecture a lot, wherein they use only just single export, that is top one or top k, that is where k equals one routing, that is one expert per token. They don't use two or three experts, they just utilize one expert, because as we discussed earlier, using one expert will have a much faster inference, right? So the advantages are user top. The router work is lower because it has to just route to one expert rather than computing for all. Now, this leads to lower communication cost. What do you mean by communication cost? Let's say you've chosen three experts. Now you have to combine the output of these experts and then produce a single output. This combining thing is known as communication cost, because you have to send these outputs from experts via GPUs and then combine it and then produce an output, right? This all contain this all leads to computation cost on the GPUs, and hence you will have, if you just choose one expert, you will have a lower communication cost. Next, expert batches also get larger and easier to compute, because you can now have individual experts trained well rather than having lot of experts. also reported four times pre-training speed over T5 XSL. In this architecture, they use a lot of stability tricks, or you would say smart optimizations to produce better results. What are they? First is the load balancing loss that we discussed earlier, where the router uses exponentials and large logits, destabilized training, selective precision, and router Z loss. What do these mean individually? First, first discuss about load balancing loss. Now again, if you were me, you would have this question, like why do we even want to train all experts on all tokens? Don't we just have to train an expert based on what it specializes in, right? Like I had this question while reading the paper. So the answer to this question is that we use this architecture while training itself. That is, we start this architecture while training. When we when we have neural networks who haven't specialized in their own domains, right? They are yet to discover what the specialty is. So hence when we just balance the load across all the experts, we can encourage the experts to gain the specialty. Mathematically, a prediction loss is nothing but prediction loss, or let's say a loss or complete loss, is consists of a prediction loss and a load balancing loss. That is this the work by Shazin on noisy Topke gating introduces a load balancing loss. Now this component, the load balancing loss, is often very small as compared to the prediction loss. What do I mean by that? Is that, let's say, even if you route a input coding token to an HR expert, the loss that it will produce will be high. The prediction loss will be high, whereas the load balancing loss will be very low, right? Due to which the router learns that, okay, I have to, during training, I have to route the tokens to all the experts, but based on what the experts have produced, this coding token should be routed towards the coding expert rather than the HR expert. So this way, all the experts have enough examples to get trained on the specialties, but the router also learns when to route which token to which expert. And just to put it in perspective, this uh, like a mathematical formula would be something like this. If I can show here, I think they don't have it here. Never mind. I'll just explain it. So the loss equals prediction loss plus some coefficient into the load balancing loss, where this coefficient will have a very small value like 0.001, due to which the prediction loss will be a larger component as compared to the load balancing component. And hence, we can efficiently train the router to route the tokens to their appropriate experts. So this was about the load balancing loss. Now, and as we discussed, router uses exponentials. Softmax uses exponentials. So when the router produces raw logits, we use exponential functions, right? In order that is, Softmax uses exponentials to exaggerate the numbers. Now, what happens is, like this brings us to the second concept of selective precision, where we keep the router in full precision and experts in B float 16. Why is that? See, there are two types of precision, FP32 and B float 16. FP32 is that full precision, like it will have around 8 to 10 decimal places something of precision, whereas B float 16 does not have so much precision. It gives the approximate values. So Let's say if we use full precision for both the router and the expert, what happens? If we use full precision, and let's say the number is something like 100.1223478 something, 10 decimal places, and then we use exponential on it. What happens is that this will produce an astronomically large number, right? E raised to 10 power something will be so large. This is one problem because computers don't have infinite memory, right? Like they can't store such huge numbers. This will lead to a lot of computation cost and just decrease our usage ability of such an architecture. Now, what if we use bfloat 16, which has a lower precision? The problem with this is that if we use bfloat 16, the numbers that have nearby logits, that is they have if they have nearby raw scores, the probabilities that the softmax will calculate will also be nearby, and hence we won't be able to efficiently train our router to guess which expert to use. So we can't use full precision in both routers and router and experts, as well as we can't use bfloat 16 in both. The switch transformer architecture uses a hybrid approach where they use rou- full precision in routers and bfloat 16 in the exports. Why is that? See, in exports you don't need full precision calculations. Experts are basically taking an input and calculating doing some computation, producing an output. Their precision does not matter so much, and hence we can use bfloat 16 in order to reduce the computation cost and increase the inference speed. Whereas in router, we do need full precision because we are calculating the probabilities, right? And even small numbers, even small differences will have will have good or better impacts on the probabilities because softmax uses exponentials, and hence this will help us distinguish two experts which are nearby logits, but vast difference in the probabilities. So that's why we use selective precision in switch transformers. Now, the next problem that this causes that, as you might have guessed, if we use selective precision in routers, and let's say the the number that we get in a router is huge, this will produce a large number after exponential, after softmax, and again we come back to the same problem of increasing computation cost. The solution to this is router Z loss, where we use some formula. Just a minute, I'll check my notes for the exact formula. It is something like Z equals log of sum of exponential of logits. In simple terms, it just reduces this large number to something small that helps us differentiate between the probabilities, but also uh, keeping the computation cost very low. So this is router Z loss in simple terms, and these three techniques is what switch transformers use to optimize and produce good quality of outputs. Using all these techniques, what do the experts learn? The encoder specializes in token groups, examples punctuation, proper nouns, shallow concepts, and decoder experts specialize less clearly. In multilingual MOEs, experts do not simply become language experts. They become proper domain experts rather than specializing in individual concepts like proper nouns or something. Now, earlier we discussed that in say switch transformers, we can have infinite scale. But is that true? That is, if we just keep on increasing the number of experts, will it increase the output or actually decrease? So, in order to understand this concept, I would like to give an example that let's say you have again 100 tasks and two interns, right? Each intern will get around 50 tasks and they can get trained well. Correct? Let's say in another case, you have 10 interns. How much will each intern get? How many tasks will each intern get? 10 tasks, right? What about the experience? The experience that they gain with by solving a 50 task versus uh, versus the experience gained by solving 10 tasks. Which one will be higher? The first case, right? Now let's say I give you 100 interns. Each will get uh, only one task. Again, the experience that they gain will be further reduced. So, so this way we do scale efficiently using a switch transformer architecture, but it has diminishing returns because as you for a fixed number of tokens, as you keep increasing the number of exports, each token will be trained on lesser and lesser number of tokens, and hence the output quality will also reduce. So hence it can be somewhat of this kind of curve where up to certain point, you gain advantage by increasing the number of experts, but after that, the output quality will simply reduce. So this is what I was talking about, where the output output on tasks like super glue and super glue record task was just plateauing after a point because the experts don't get trained as efficiently as they would if there were less number of experts. So up to a certain point, more experts improve sample efficiency and speed up, but then gains diminish after a very large expert count. Also, you have to load these experts on VRAM. So this will increase the computation cost. So this was about it for today. Let's see. I hope you enjoyed this video. Let me know the feedback for this video on the comments in the comment section, and let's continue with fine tuning in the next video. This is a very interesting concept with a practical as well. So let's see, let's meet there. Thank you.